So what we're going to do is we're going to have a look at an FSAE test example to show you the new Fluent meshing workflow, and we're going to actually look at solving the model and some post-processing side of things as well. What we're going to do first is bring up the Fluent solver. We're going to be solving in double precision, entering into meshing mode, and in this computer I've got 4 physical cores, and I've also selected the correct working directory which has my geometry in it as well. And I'm going to press OK, and let it start up. So this is the Fluent meshing interface. We've got the traditional tree interface on the right hand side next to the tab, but we're going to have a look at the new watertight geometry meshing workflow. We're going to select the geometry that we wanted to actually input, select the correct units as well, and import the geometry in. Now that the geometry is important, we can have a look around at it. We can see here that we've got the wing that we've imported in, and we're going to start to add our sizing controls as well. First one is just going to be a front wing sizing. We're going to add a 5mm sizing and assign it to the front wing itself. The next one is going to be a body of influence. It's going to be around a 50mm sizing, and we're going to add that to the body. The body's a separate body that's come in. Creating our surface mesh, we're going to keep the minimum to 1mm and keep the maximum to 150mm. Keep curvature and proximity. We're going to change the curvature normal angle to 9 in order to pick up the curvature around the front wing, and we're going to have 4 cells across the gap. Now that the surface mesh is created, we can have a look at it. We can move the model around. If I right click and hit control at the same time, it'll hide a face. So I can go in, have a look at the curvature, have a look at we've got 4 cells across the gap as well. And we can see at the bottom we've got the sizing that's been respected. We're going to start to describe the actual geometry. So it's a fluid with no voids, and we've got no fluid-fluid interfaces. So we've done that, and what we're going to do is also describe the label. So we've got a front wing, that's the wall. We've got a ground, that's a wall as well. An inlet's the pressure inlet. We've got a pressure outlet, temperature plane, and this wall as well. What we're going to do for this particular case is just change it over to a pressure inlet, because the current Fluent meshing workflow will actually create a inflation layer, which we can change later on in the following versions. But what we're going to do, leave this as a wall. There's no inflation that's going to be created, and we're actually going to change it in the solver afterwards. We're going to update the fluids regions. We're going to tell the enclosure that it's a fluid as well, and we're going to have a look at our surface mesh. We're going to be using the last aspect ratio. We need around 10 layers. We're going to transition to around a 20%, which is fine, and we need a 0.005 first layer height, which is 0.5 mil. In this particular case, we're going to be having a look at the new Fluent meshing mesh type, which is a polyhex core, and we're going to create the volume mesh. Now that the mesh has been created, we can have a bit of a look at it. We can see that we've got boundary layers growing on the floor as well as the wing as well. If we look, we can see that we've got all the layers that we need around the trailing edge. Now that we've got our mesh created, let's go to the solution. And we can display the mesh just to double check everything's come in exactly as we expected. We'll go through and add a turbulence model. I'd recommend either the K-Omega SST turbulence model with curvature correction, or the K-Epsilon realizable K-Epsilon with the enhanced wall function. Let's go over to our boundary conditions, and let's change the inlet to an inlet of 20 meters per second. And these are the 2 walls that were previously changed over from wall to inlet. We're going to change them back to walls here and leave them as specified shear, so there's a slip condition there. We're also going to have a look at the ground, and the ground, as there's no boundary layer it's actually being created, though there is a moving wall at the same speed, and it's going to be translating in the positive x direction. Having a look at the methods, I changed the scheme over from simple to coupled, and leave the numerics as is. We'll go over our report definitions, and we'll just add a lift definition for the front wing. We can then have a look at our calculations, and in this particular case, we'll just run it for 100 just to show you guys how it's done. Um, when you're actually running it though, you'll probably want to run it for 2 to 300. You want to check for residuals to make sure they've dropped by a couple of orders, but also check the force monitors to make sure that they've stabilized as well. So I've actually went back, and instead of 100 iterations, I've let it go for 500. At the moment, it's sitting at around 552, and I've stopped it. We can have a look at the residuals. We can see that they're oscillating around a mean, and so is the actual report monitors as well. Now, with the report definitions, when we set this up, we actually also set up a report file, and if we go to our reporting our directory, our working directory, we can see that we've got a .out file with the name of it here, and we can see that we've actually got everything written out for us. If we wanted to, we can take that file to Excel and do some post-processing in order to understand what the mean is, what the standard deviation is, and what the percentage variation is over time. Now, this pretty much tells me that we need to actually refine the body of influence, and I know that because I've done a mesh study before, and I know that it's required to do something a little bit finer. But that's something we can do later on. Let's have a look at the post-processing side of things. So what we can normally do is we can draw the mesh if you wanted to. We can kind of have a look at what it's looking like. What I'll also normally do is draw a plane on this as well. So what I'm going to do, I'm going to go up to my surfaces here, create a plane. I'm normally happy with just going point and normal, and we can see that we want it normal to the Z direction. Got the triad on the bottom right. And if we go back to our mesh again, we can have a look at the actual plane. Right. Now let's have a look at the contours. One of the things I'll normally pick up is we'll have a look at what the static pressure is on the wing. So we just want to do a sanity check. We're expecting lower static pressure at the bottom. We've got higher static pressure at the top, so it means that we're making downforce. And we've got this very low region around here, around the end plate, where we've got this vortex being created. So I can also have a look at my total pressure as well. What we'll also do, we'll have a look at the Y plus value. Again, so it goes from a max of around 30, which is what we expected. We can have a look at where it increases. We can see the Y plus increases with local velocity, again, as expected. And we can also have a look at the turbulence viscosity ratio. So this is something that's required in order to pick out if you've actually if you've selected the correct amount of boundary layers. So let's display that, and we'll change it until we can see the gradient around the boundary layer. As expected, we're seeing this transition from a blue region, so a light region, the viscosity is increasing, so we're in the turbulent region, and we're going out to the outer region as well. I'll have a link in the description for a read of a blog post that was created. So one of the things that I also normally do is create a scene sweep animation of the total pressure, so we can have a look at the energy down the line. So we're going to sweep around the x-axis. When we look at our contours, I'm just going to select the ground, and we're going to select total pressure going from a negative of 100 to a positive 100 as well. I'm going to go from 0 to 1, and initially we're going to go for 10 frames. And we can see we've got an animation. And if we slow it down, we can see what the total pressure is. If we replay it, and we can keep an eye on the bottom right, we can see a vortex being shed off the end plate and growing as it moves down the flow field. So it's exactly as expected. We can also clearly see that we don't have enough layers actually picking up what the shape of the vortex is looking like. So that's one of the reasons we're having oscillations in our residuals. We can have a look at the force monitors and start to output some force values if you wanted to as well. We can write all these out. And we can also have a look at things like isosurfaces. So if we display the front wing first. again, we can go back. We can look at the low pressure regions around here as well. We can pick up what the vortex is and what it's doing. And when we've got more complicated features as well, we can have a look down the line. So what we're going to do is go File, write the case and data file, and that's our simulation.